students, and welcome back to Study Room. So I told you in the last lecture that we are going to continue and study the topic heating effect of current. Now you might ask, why is there a heating effect at all when there is some flow of current? Well, for that I'm going to take you back to the original circuit that we studied. So we got to know that the battery actually is responsible for maintaining the potential difference across the circuit. Then we also learned that current, or anything for that matter, not just electric current, water current, wind current, air currents, all these currents flow when there is a difference in something between 2 points, right? So electric current flows when there is a difference in the potential between 2 points. So the difference in potential is brought about by the battery in case of a circuit, right? So there is actually, this is a new thing that you're going to learn. There is actually some chemical reaction. You don't need to know the equation for that and everything. You just need to know that there is a chemical reaction that takes place inside the battery, which gives rise to the potential difference that the battery maintains. Now, because this battery is continuously releasing or expanding or using its energy to maintain this potential difference, to maintain anything, if you have to hold like a rod up above your head, you have to expand you have to basically use your energy, right? No work happens without any energy, and the battery is doing the work. Here, work, I'm not referring to the physical work, like the work energy work. I'm referring to just, that's why I don't want you to use any formulas. I'm just referring to any kind of work, like walking is a work, like any kind of job that it's doing. So what is the job of the battery? What work is the battery doing? It is maintaining that potential difference. So it is obviously using up its energy. Okay, you can relate this to the physical work too. So because it's expanding its energy, we know that energy cannot be created or it cannot be destroyed. It can only be converted from one form to another. So just think about it. This energy that is being used by the battery to maintain that potential difference, where is it going? It has to go somewhere, right? So one way that it can be used is that energy can be used to run some appliance like our fans. That fan is actually using that energy of the battery or whatever source of power or voltage source that it is connected to. Now, another way is that the rest of the energy, some of the energy say is used up in rotating an object like a fan. Now, the rest of the energy is given off to the environment in the form of heat. This is the heating effect of current. Okay? And say if there is in the circuit, there is not any appliance connected like the fan. That means that there is no appliance that can actually rotate or move and use up some of the energy from the battery. Say it's just resistors. So what is going to happen in that case? All of the energy that has to be used up somewhere is given out in the form of heat. Unless and until there is something like a fan or some other appliance that can be moved or rotated or something. So that heating effect, where it is purely resistors connected in a circuit, that heat that is generated in that kind of a circuit can be used to do other things like our electric heater or our iron. What are those appliances? They are purely meant for producing some kind of heat, right? Your press is meant for producing heat, your electric heater is meant for producing heat, and so on. Okay, so I hope that is clear to you why there is actually a heating effect due to current. Now, what is the common principle of working behind these electric appliances? It is actually the heating effect of current. Okay. So in all these appliances, they are just purely resistors that are connected to the circuit, so that all the heat, all the energy that is used by the battery is used up in producing heat, like your oven which you use to bake stuff, or your microwave which you use to heat stuff, or your press, or your iron, and your heater. So all of these appliances use the principle of heating effect of current. Okay? Great. Now, the dissipation of heat in a resistor. So, this is just an explanation in proper words of what I already told you. So, let's read here. It says that in a purely resistive electric circuit, the source energy continuously gets dissipated entirely in the form of heat. What does this mean? Source energy. What does source energy mean? What is the source? Source is the battery, right? And energy. So what does source energy mean? That the energy that the battery is using up to maintain potential difference. So this source energy basically means that the energy that the battery is using up or sending out, that energy is used up in a purely resistive. See, here it's written in a purely resistive. What does that mean? That it is purely a collection or a combination of resistors. There is no appliance like a fan that can actually like move and use up some of the energy in that way, so that the rest of the energy can be dissipated in the form of heat. No, here all the energy is dissipated or let out in the form of heat in a purely resistive circuit. So the source energy gets dissipated. Dissipated basically means given out to the environment. Okay, this is what dissipated means, in the form of heat. This is known as the heating effect of electric current. Okay, so I hope this is clear now. Now, the Joule's law of heating. Now, for this, I am going to tell you to look at the figure that is given to us. So, we can see that this current I is flowing in the circuit, right? And there is one resistor R, and suppose that this resistor has a potential difference of V across S. So you remember that we studied the formula of potential difference to be that the work that has to be done to take a coulomb of charge, like work upon charge, that work that has to be done to take whatever coulomb of charge has to be taken across this potential difference. So we got the formula as V equal to W by Q. So if I send this Q to this side, so we get work is equal to V into Q. So basically, what are we saying? That this charge, say Q, has to be taken across this potential difference. Can you see here this voltmeter? Suppose the voltmeter reading is V. That is what, it can be any value. It can be 2 volt, 3 volt, 5 volt. So I am just taking a common general term as V. So if V is the potential difference across this resistor. So by the definition of potential difference, we know that how much work has to be done to take a coulomb of charge or any coulombs of charge across that potential difference. It is W by Q by formula. So if we want to know the work, so we can just keep work on this right hand side and we can send Q to the other side. So we get W is equal to V by Q. Sorry, W is equal to V into Q. Now, what does this W mean? This W basically means that the battery or whatever the source of potential difference is, the source, initial source, the main source, it has to do a work. See, look at this. It has to do a work which is equal to VQ to take this Q charge from one point to the other where the potential difference is V. That is from point X to point Y, right, across R. Now, we know what is the formula of power. Do you remember what power is? You have studied power is nothing but work done upon time. You have studied this formula before. So, we are going to use this formula that power is work upon time. So, now we have got our work as V into Q, right? So, what is power? Power is nothing but work upon time. So, power is work which is VQ. So, I can write VQ in place of this W. So, I'll write power is work which is VQ here upon time. Now, what is this quantity? Q upon time. The charge that flows through an area upon time, what is that? Charge per unit time. What is that? Charge that is flowing through one particular area in a unit time, that is known as current. So you remember we did this right at the beginning of this chapter. So power basically becomes equal to V into Q by T is replaced by I. So this much is clear, right? So this formula is given rise to P equal to VI. This is also a very important formula that is going to be used for numericals. So this much is clear to you that the potential difference is work upon charge. So work is just equal to potential difference into charge. We just rearrange that formula, and we know that power is work upon time. So we did work, which is VQ upon time, and Q by T we replaced by I, because we know Q by T is the current, or I. Now from this formula again, what is, we know that work and energy are actually equal, right? Because the work can only be done by the stored energy. So the stored energy determines the work, and how much energy is stored, only that much work can be done, and they both have the unit joules. So work and energy are actually equivalent, just in different forms. Energy is the stored form, and work is the form in which some kind of action is being done, or that energy is being used. So now we come back to this formula, power is equal to work into time. So if I take time to this side, what happens? Work is equal to energy. So what happens here? Power, I'm representing power by capital P, okay? Power into, what happens here? Power is work upon time. We take time to this side. So power into time is work or energy, right? Because work and energy are equal, we just said. So because we right now we've talked about energy so much, about the energy expended by the battery, or the energy that is being used up by the battery. So I am going to use the energy term. So what does this mean? Energy, or E, is nothing but, what happens, just forget this W right now. I just wrote it to tell you that it is equal. So this energy is equal to what? Power into time. Power into time. And come back to this formula. Here, what have we written? Power is equal to V into I. So I replace power by V into I. So energy is equal to V into I. Power is replaced by V into I, and what is left here? Into T. So basically energy is equal to VIT. And what did we study? We studied that in a purely resistive circuit. So here it's a purely resistive circuit, just one resistor, right? So in a purely resistive circuit, all of the energy expended by the battery is given out in the form of heat, right? Like our appliances like microwave, ovens, or heater and stuff like that. So this energy, you can write this energy, because it's a purely resistive circuit, this energy is given out as heat, which is represented by capital H. Okay, so therefore you can clearly replace this H by E, because this energy is actually replaced by heat. This energy is given out in the form of heat to the environment. That is how we get this formula. H is equal to V into I into T. Actually, what the formula is energy is equal to V into I into T, but because it's a purely resistive circuit, all of this energy is given out in the form of heat. So we get our formula H is equal to VIT. And we also got another important formula from here. P is equal to VQ by T, or VI. Okay, these are all important formula for numericals. Okay, moving on. Now, we're going to study the Joule's law of heating. So, we're going to use the equation that we just derived in the last slide. We learned that H is equal to VIT. We learned this. Now, what did we learn in Ohm's law? Ohm's law says that V is equal to IR, right? Now, if this is equation 1, then we write this is putting this relation in equation 1. EQN is what I am representing, equation, I am writing it in short form. So what happens when I put V equal to IR? I replace V by IR in this equation. What happens? H is equal to V. So I write IR into another I into T. Now, what is I into I? How do we represent it as? What is 2 into 2? It is 4, right? And 2 square is 4. How many times we multiply this number? If it's 3 into 3 into 3. So it is 3 to the power 1, 2, 3. 3 times, so 3. So it's basically whichever number you are multiplying as many times, that is the power. So here how many times are we multiplying I? 2 times. So this becomes I square. So that takes care of this, and this I. What is left? R and T. So we write R T. So here H is equal to I square R T. So what can you see here? That this H is actually proportional to I square. This H is also proportional to R, and this H is also proportional to T. So that is all the Joule's law of heating says. Look at this here. This law implies that the heat produced in a resistor, that is H, is directly proportional to the square of the current. What does that mean? I square, square of the current in the given resistor. Okay. Directly proportional to resistance, obviously, and directly proportional to the time for which that current flows through that resistor. Right? So for this, there is a resistor R. There is some current that flows because of this voltage or potential difference or this battery, and we are looking at time T. So this current I flows for a time T across this resistor R, and it produces the heating effect H. So H is equal to I square RT. That is all the Joule's law of heating says. Okay. Here we are saying, even though there is no proportionality sign, we are saying proportional to because it is actually equal. That means, what does proportional to mean? Proportional to means that when one increases, the other increases. So here, because it's H is equal to I square RT, no matter what I increase, if I increase T, H increases. If I increase R, H increases. If I increase I, H increases. If I decrease R, H decreases. If I decrease I, H decreases. If I decrease T, H decreases. So that is how I mean to say that it's proportional to all of these. Okay. So now we have an example. Okay, so the question here says that an electric iron consumes energy at the rate of 840 watts. At the rate of 840 watts when heating is at the maximum rate. Okay, and 360 watts when the heating is at the minimum. Okay, and the voltage that it's connected to is 220 volts. So it is asking what are the current and the resistance in each case. Now, I'm just going to divide this into case 1 and case 2 so that it's clearer to you what we are actually doing here. Look, so the case 1, what does it say? That heating is at maximum, heating maximum, right? And it is given that an electric iron consumes energy at the rate. Now, what is this 840 watts? Is it energy? No, because what is the unit of energy? Unit of energy is joules. It is not joules, so this is not energy. So it is saying that energy at the rate. What does rate of consumption of energy mean? Do you remember what is energy, or energy same as work? So what is work? And rate always means that divided by time. Rate always is in respect to time, or how much time it is taking to do something. So basically, rate of consumption of energy means energy upon time or work upon time. So what is work upon time? Work upon time is nothing but power. So the unit of power is this capital W, or watts. Okay, so this is nothing but power. Similarly, this is nothing but power. So here we have heating is maximum in case 1. Power is given. So here the power is given to us as 840 watts. That's it. That is what is given to us. And we know that the voltage is 220 volts. That is the same for each case. So in case 2, this is what I am writing the given. Okay. And in case 2, what are we given? Heating is minimum. Right? And in case 2, what is the power consumed? It is 360 watts. So what did you learn new in this question you learned that the consumption rate of energy is known as power, or consumption rate of work or work upon time is known as power. So you need to pay attention to the use of words. It doesn't just say that the energy expanded or the energy consumed is 840. It says the energy is consumed or expanded at the rate, right? So that means power. Now, what else is given here? V is given to you as 220 volts only. Okay, great. So now we'll solve this. So for case 1, what do we have to find? We have to find the current and resistance in each case. So case 1, we are solving for case 1 for current. We are solving for current. Now, what do we have? We have P and we have V. So is there any way I can find I? Yes, I told you there is a very important formula. P is equal to VI. So I am going to use this formula, and from this formula I have I is equal to P upon V, right? What is P here in the case 1? It is 840, and what is voltage? It is 220. So the zeros get cancelled. If I am cancelling by 2, 11 and 42, right? So what is 42 divided by 11? When you do this division, it comes out to be 3.82 amperes. So this is your current for case 1. Now, for resistance. Now we have to find the resistance for case 1. Now which formula is coming to your mind? You have I, you have V, you have P. Is P going to be used in finding resistance? No, right? We only need V and I. We can simply use Ohm's law and find the resistance. So, we're going to use Ohm's law. So, you can write here, using Ohm's law, we have V equal to IR. We have V is equal to IR, right? So, what is R? R is equal to V upon I, right? And what is V for this case? It is 220 upon, we got I as 3.82. When you divide this, you get 57.61. So I have divided it. You divide it for yourself and check that the resistance comes out to be 57.61 ohms. So you are done for case 1. Moving on to case 2. Same thing we have to do for case 2. Same formulas you have to use, so it's not tough for you anymore. So we have to find current. So we use P equal to, here we use V equal to IR. So we use P equal to VI. So what does that give us? We have the power, we have the voltage. So we find the current is nothing but T, which is 360 watts in this case, upon the voltage, which is same as 220 volts. So I divided by 2. So 11 and 2 1s are 2, 1 16, 2 7s are 14, 2 8s are 16. So when you divide it, it comes out to be 1.64 amperes. This is your current for case 2. Similarly, when we calculate for R, we use V equal to IR. Whenever you write V equal to IR, please write using Ohm's law V equal to IR. Get in the habit of writing all the sentences and all the statements that is required. Okay. So V equal to IR. So R is nothing but V upon I, which is equal to 220 upon 1.64. And I have done my division here. It comes out to be 134.44. So for all these divisions, I might have made some mistakes somewhere. So please do all the calculations by yourself. Never believe what the teacher tells you in case of calculations. Anyone can make a mistake. It can be a very honest human mistake, right? So always do the calculations by yourself to cross check. Okay. Okay, moving on. So the next question says that 100 joules of heat is produced each second in a 4 ohm resistance. Find the potential difference across the resistor. Okay, so I write the given, what is given to me, heat, or we represent it as capital H is given to us 100 joules. Okay, is produced per second. So time that we're talking about here is actually 1 second, right? We're talking about 1 second here. And resistance or capital R is given to us as 4 ohm. Find the potential difference across the resistor. We have to find V. Now, what is coming to your mind looking at this H, time, resistance? What is given to us? We are given H, we are given T, we are given R. So think about it. You have H, you have T, you have resistance. What is the first formula that comes to your mind using H? Using H, R, T, the formula that should come to your mind is the Joule's law of heating formula, which is H is equal to I square RT. Even if you don't know any one of them, just write the formulas. Whenever you see some variables, that's why I always say it is very important to write these given while you're solving the question, because as soon as you see these symbols together in one place, immediately you're going to think of the formulas that use these symbols, and using those formulas you will easily get to your answer. So you write in the solution that using Joule's law of heating, H is equal to I square RT. Okay, now you might think we don't know I, no problem. Do we know H? We know H, H is given to us. Do we know R? R is given to us. Do we know time? Time is also given to us. So can we find this I square? Absolutely, shouldn't be a problem. So okay, we find I square. What do? I square is kept on the RHS. We send R and T to the denominator on the LHS. So I square is nothing but H upon RT, right? And what is our H? H is 100. What is R given to us as? R is 4 ohm. And what is time given to us? It is given as 1. So what does this come out to be? 100 I square is equal to 100 upon 4. So if I divide this by 2, so this comes out to be 50, and 2 we divide it again, it comes out to be 25. So we get I square is equal to 25. So what is I? I is equal to root 25. What is 25 the square of? Which number has a square of 25? It is 5. So our I comes out to be 5 amperes. We have I, but did we have to calculate I in the question? No, we had to actually calculate the potential difference. So now, if you had thought, if your thought process had been, oh, there is no formula that has potential difference, H, I, R, T, all of that. So then you would have been stuck, because then you wouldn't have been able to think of a formula. So don't directly go to what you have to find. There might be something that you can find first, and then using that you will get to your final answer. So now that you have your I and you have to find your V, what is the formula that comes to mind that has V, I also have R. Obviously, it is going to be Ohm's law. So V is equal to I into R. So therefore, V is equal to, what is I? 5. What is R? 4. So I is 5 into 4, which is 20 volts. Simple. So always go step by step. Never be afraid looking at the question only. Okay, great. Okay, now let's move on to the next question.